Okay, so far in this chapter, we saw how an alkyl halide can react in an SN2 pathway if you have a strong nucleophile present, or it can react in an E2 pathway if you have a strong base present. What happens then if you don't have a strong nucleophile nor a strong base to promote those bimolecular pathways? Remember, bimolecular means you have that substrate, the alkyl halide, and the reagent, either the strong nucleophile or the strong base, together in the rate determining step. Well, the answer is a unimolecular pathway that is solely dependent on the substrate. So in this video, we will dive into this pathway. Let's explore what happens when a tertiary alkyl halide that dissolved in a solvent and nothing else. For example here, ethanol. Notice that ethanol is neither a strong nucleophile nor is it a strong base like its counterpart, the ethoxide ion. Because of this, you would not expect an SN2 or an E2 reaction to occur. Yet we do observe a substitution product and an elimination product. So what is going on here? Let's explore some features of this reaction. The first is looking at its rate law. It turns out its rate law is solely dependent on the concentration of the substrate alone. That is, it is a first order reaction. So this means it cannot be an SN2 or an E2 reactions for those for second order reactions. So instead of the bimolecular pathways, it turns out that this substrate, being a tertiary alkyl halide, is more comfortable undergoing a unimolecular pathway, with its first step known as an ionization step, where there is first a loss of leaving group, yielding a rather stable carbocation, this tertiary carbocation. Now with this carbocation, it can be captured by the solvent either via a substitution-like reaction or an elimination-like reaction. Namely, these processes are known as the SN1 reaction and the E1 reaction. Let's take a closer look at each of these pathways one at a time. Let's start with the SN1 mechanism. As we have stated, the first step involves the loss of a leaving group, giving us our carbocation, at which point the ethanol can serve as the nucleophile to come in for that nucleophilic attack. This step is also known as solvolysis, as a solvent molecule is involved in that nucleophilic attack, even though it's not actually breaking the bond of the carbon and the leaving group, as the name lysis implies. It is still considered a solvolysis because ultimately it does replace that leaving group. The product of that step is an oxonium ion intermediate. Basically, it's an intermediate where the positive charge is on the oxygen atom. In our last step, the solvent molecule acts as the base to deprotonate the oxonium ion, giving us our neutral final product, the substitution product. Let's go ahead and take a look at the energy diagram of this mechanism. First, we have the reactant forming that first intermediate, the carbocation. Then a second step forming the oxonium ion. Then finally giving us our substitution product. Notice that the rate determining step would be the step that involves the highest transition state. In this case, it is the first step, the loss of the leaving group. Because this first step is the principal step that determines the rate of the reaction. You can increase the rate of this reaction if you can minimize the energy barrier of this first step. And you can do that by stabilizing the first intermediate, the carbocation. And so because of that, this whole reaction is solely dependent on the substrate itself. This nucleophilic substitution reaction is called the SN1, where the 1 here points to the unimolecularity of this pathway. And again, notice the parallel of this reaction with the SN2 reaction. They both involve a loss of leaving group and nucleophilic attack. In this SN1 reaction, it is a stepwise process compared to that of the SN2 process, which happens in a concerted fashion. In an SN1 pathway, there is usually one extra step, however, that last proton transfer step to give us our neutral product. The E1 mechanism is very similar. First, you have a loss of leaving group, again giving us our carbocation intermediate. Now instead of doing a nucleophilic attack, the ethanol can also serve as a base, a weak base, extracting that proton and forming that double bond, leaving us an alkene as the product. Again, in this state, there is a carbocation intermediate, and the highest transition state, which determines the rate determining step, is that first step. So the name of the mechanism, E1, highlights again the fact that it is a unimolecular pathway. Notice again that this mechanism is very similar to the E2 mechanism, where you do have that loss of the leaving group and the proton extraction. It's just that in this unimolecular pathway, it is happening stepwise rather than a concerted fashion. Now let's take a further look at some evidence that support for this stepwise mechanism. First, let's take a look at this example. If you have this alkyl halide in just water and heat, it will not have an E2 or an SN2 reaction. However, elimination and substitution products are possible. For example, we can expect this substitution product. Interestingly though, this other substitution product is also observed. How can this be? The answer to it is that it is the product of a rearranged carbocation, which is evidence that a concerted mechanism is not involved if a carbocation is indeed involved. So let's take a look at this mechanism. First, you have a loss of a leaving group. Now, with that carbocation, the water can come in and attack at that site to give us our first product. Or you can have a hydride or methyl shift. When you have a hydrogen available, you will opt first for that hydride shift, giving us a more stable tertiary carbocation, at which point the solvent, water, can do a nucleophilic attack at that new reaction center, giving us our oxonium intermediate, which then follows by a proton transfer step to give us our final product. The take-home message here is that because there is a rearranged product, it means that this reaction would transition through a carbocation, meaning that it cannot be a concerted mechanism. Further evidence for the existence of this unimolecular pathway. The second important note here is that when you are dealing with an E1 or an SN1 reaction, when you are predicting the product, also include the product that is a result of a rearrangement, especially if that rearrangement is driven by a more stable carbocation. Recall that the rate of the SN2 reaction is increased by a polar aprotic solvent. It turns out it is the opposite in an SN1 reaction. In an SN1 reaction, the rate is increased by a polar protic solvent. Let's explore why. Remember that in an SN2 pathway, the starting material are ions. And so because of the ionic nature of the starting material, the reactants, it is destabilized by the polar aprotic solvent, so its energy level is raised. Because of that, its activation energy is decreased, making it a more favorable reaction. In an SN1 reaction, however, you do not have that ionic starting material. In this case, if you have a polar aprotic solvent, you are not going to destabilize the starting material, but you're going to destabilize the ionic intermediate instead. Remember, there was the carbocation intermediate, which is essentially an ion. As you increase the energy of the intermediate, but not increase the energy of the starting material, your reaction profile will look like this. Notice in this case then that your energy of activation is much higher in the polar aprotic solvent. So again, in the SN2 reaction, you will see that the polar aprotic solvent speeds up the reaction, while in an SN1 pathway, having a polar protic solvent will speed up your reaction. As I have alluded to in the rearrangement section of this video, the nature of the substrate will have an effect on the SN1 and E1 reaction. So let's explore this a little bit further. Because your reaction depends on the rate of the first step, the loss of the leaving group, so having a good leaving group will also increase your reaction. So the stability of your leaving group dictates the reactivity of the SN1 and E1 reaction. So having an iodide is better than having a bromide, is better having than a chloride. All the way on the other end, remember that the fluoride is not a good leaving group. It would also mean that it will not be a good substrate. Besides the leaving group, the degree of substitution on the alkyl halides is also very important. In fact, primary or secondary alkyl halides will not be good candidates for the E1 or SN1 reaction, but only the tertiary alkyl halides will, as it will transition through a stable tertiary carbocation. Now there are exceptions. For example, if you are in a benzylic position, the carbocation is stabilized by the resonance of that aromatic ring. Or if you transition through an allylic carbocation, again, there will be stabilization from a resonance of that pi system. However, make sure to never transition through a carbocation where the charge is on the sp2 hybridized centers. Actually, there's one curious exception to this rule. Let's take a look at this example here, where we have a primary alkyl halide, yet there still be an SN1 product. And interestingly, there's only one substitution product. The product resulting from a rearrangement is observed. So why do you think this is? Let's take a look at the mechanism. As we suspect this must be an SN1 reaction, so we would have to first draw in the loss of the leaving group. Now, seeing that carbocation intermediate, what stands out about it? Hopefully you've noticed that it is a primary carbocation, which is highly unstable and therefore will not be able to exist. So this pathway is quite unlikely. And so the water can't just do a nucleophilic attack at this site to form this unarranged SN1 product. However, an SN1 reaction still occurs, so how can that be? It turns out a methyl or hydro shift can occur simultaneously as the loss of leaving group. You can think about it almost as a methyl shift that assists in kicking out the leaving group. So when you do that, you see that you have created a tertiary carbocation, which we know is stable and can exist. So this pathway is indeed possible, allowing for the rearranged substitution product to be made. Alright, so in summary, these are rare exceptions, but in general, when we think about an SN1 or E1 reaction, we want to think about a tertiary alkyl halide substrate. Now let's touch base a little bit on the regiochemistry of these reactions. As you can see here, if this substrate were to undergo an E1 reaction, it may involve multiple elimination products due to the fact that you have non-distinct beta protons. For example, you can get the more substituted product, the Zaitsev product, or you can get the less substituted product, the Hofmann product. It turns out there's no way of controlling it if you are doing an E1 reaction. The Zaitsev product is always going to be the major product no matter the solvent that is used. And remember, you are also in competition with the substitution reaction. There's no avoiding the fact that you have a combination of products when you do a unimolecular reaction. Oftentimes, the elimination product will be the major product as compared to the substitution product, but that has to be determined on an individual basis. And as we have said, the Zaitsev product will be favored over the Hofmann product. And if there is stereoselectivity, then the E isomer will be favored over the Z isomer, simply because it is more stable. So all of this just presents to us that you can't have much control of the unimolecular reaction. So in a practical sense, the unimolecular pathway is quite useless to the synthetic organic chemist most of the time. But we still need to learn it, as it will be useful to some instances we will see in the future. Okay, and lastly, before we end our discussion on the unimolecular reactions of alkyl halides, let's talk about the stereochemistry of the SN1 reaction. Recall in an SN2 reaction, when you do an attack, there is something called the inversion of configuration. In an SN1 reaction, however, it is quite different. So again, with the first step of the loss of leaving group, it gives us a carbocation intermediate. But remember, what is the geometry of that carbocation intermediate? It would be a trigonoplanar. Because of its trigonoplanar geometry, we see that that carbocation has a p orbital that can be attacked from both sides during a nucleophilic attack. For example, this nucleophile can come in on the back side, much like that of an SN2 reaction, and give us one product, what we are familiar with as it is the inversion product, similar to the SN2 reaction. Or it can come from the front side of the molecule, giving us a molecule that has the same geometry as our starting material. Hence, we call this the retention of configuration. So theoretically, both of these have an equal opportunity of happening. So you would get a 50-50 mixture of the inversion product and the retention product, as opposed to an SN2 reaction where you have 100% of the inversion product. So again, this is one extra evidence for the existence of the carbocation as an intermediate in this pathway. In reality, it is not exactly 50-50. It is skewed a little bit towards the inversion product. You don't get 100% inversion, but you get a little bit more of inversion than retention. Now, why is this? Remember, you still have that bromine that just left momentarily from that substrate. So it is sticking a little bit closer on one side of the carbocation than on the other. Because of this, that front side is still a little bit blocked, sterically hindering the attack of the nucleophile, therefore favoring a little bit more of the backside attack still. Alright, wonderful. So that completes our lecture on the unimolecular reaction.